Monte Carlo simulation is too slow. It certainly can be too slow sometimes, especially when our goal on a trading desk is to quote prices consistently and efficiently. We already know we need to go beyond Black-Scholes. In the past couple weeks, I've been talking about the idea that the Black-Scholes model is insufficient for quoting prices on a trading desk, and we extended the idea to this Heston stochastic volatility model, which can better capture the dynamics observed in a market implied volatility surface. But we also talked about how there is no closed form solution to the prices in a Heston stochastic volatility model. Well, fret not, because in this video we're going to look at the fast Fourier transform, specifically an inversion technique available to us to recover the prices under a Heston stochastic volatility model very, very quickly. This will allow us to consistently and efficiently quote prices for our trading desk. My goal is to distill several years of probability and statistics, math, and quantitative finance into this one video to save you the number of headaches that I've had putting the pieces of this puzzle together myself. So what we're going to do is we're going to start with the idea of options. We're going to look at Black-Scholes. We'll talk about why it's insufficient. We'll talk about Fourier transforms. What the heck are they? We'll talk about characteristic functions from probability and statistics, how they're related to Fourier transforms. Then we're going to look at the work by Carr-Madan. We're going to look at how we can recover option prices via the Fourier inversion. And then we'll wrap up with some closing thoughts and future topics. As always, this Jupyter Notebook will be available in the description below. I will also post it on the Quant Guild library on GitHub, where you can find all of my Jupyter Notebooks and associated YouTube videos. So if you just want the code to be able to price options in this framework efficiently, you can just go ahead and check out the link in the description. Moreover, at the top of this Jupyter Notebook, I have related Quant Guild videos if you want to understand any of these topics on a deeper level, or maybe you need some background, videos in stochastic calculus, applications sitting on a trading desk of these models, statistical bases for pricing, and of course, why the expectation is sufficient in practice for generating P&L. And lastly, as we get started here, if you're interested in mastering your quantitative skills, check out quantguild.com. We have over 90 quant lessons, fully worked interview questions, an adaptive practice engine that scales with your skill level, applied trading games, and much more. So if you're interested in supporting the channel so I can continue to create free videos and open source resources just like this one, check out quantguild.com. Without further ado, let's begin putting together all of the pieces of the puzzle to understand Fourier inversion for pricing options in a Heston framework. Now that sounds crazy, but by the end of this video, that statement will be crystal clear. We're going to start with this idea of an option contract. Option contracts and pricing are fundamentally what financial engineering is all about. We're trying to figure out how much we should pay for this thing today. And we don't know. It's random. So we have to assume a whole bunch of things and create a model. And the best models are going to be ones that capture as much variability as possible in the empirical prices that we observe, while saying as little as possible about the true distribution. We don't want to make too many assumptions such that the prices that we're producing are just completely impractical. So let's get started with this idea of an option contract, right? An option contract is going to give the holder the right but not obligation to buy or sell an underlying asset at some point in the future at a predetermined price. Okay, what does that mean? Well, at some point in the future, maybe it's a month from now, maybe it's 2 months, maybe it's a year from now, if you tell me the stock price, I can tell you how much I would pay you based on that option contract. So let's say 1 year from now, we have this option contract and the underlying asset is 120. Well, in that case, I would have made $20. Okay. What if it was 80? Well, in that case, I would make $0. So we know based on where the stock price ends, how much we are going to receive from the option contract. But we don't know where the stock price is going to end. So what we have to do is we have to assume some sort of model to account for this randomness. And the Black-Scholes model is going to assume what's called a geometric Brownian motion, and that is the dynamics governing the stock price process. Okay, so if we have this idea of randomness, and we know that wherever the stock price ends up is going to be random, then what is our best guess in the face of this randomness? Well, the best guess that we have in the face of this randomness is going to be the expectation, the simple expectation. So whenever we're trying to figure out how much we should pay for a contract today, we have to use the expectation. We don't know what state of the world we're going to be in. We don't know if the stock price is going to be 120 or if it's going to be 60. We don't know. So the best that we can do is take the expectation. So what you see here is how much we should pay for this option contract is actually written in terms of an expectation. So there are a couple of other moving pieces going on here. It's a risk neutral expectation. We have a discounted risk neutral expectation to account for the time value of money, but we can ignore that for now. The real idea here is that as we are trying to determine what to pay for this particular financial instrument, we are accounting for the randomness by assuming some sort of model. Black-Scholes will assume a geometric Brownian motion, and we will take the expectation, and that will be the best that we can do to produce a fair price for this contract today. Believe it or not, this is actually very easily visualized. The solutions to both of these equations are visualized by this chart. So if I run this chart, you'll see I'll get a different stock price sample path, right? And the option contract is going to pay out based on where the stock price ends. So here it ends very, very high relative to the strike price, so I receive a payout over here. If I was to run this again, you'll see it ends lower than the strike price, so I don't receive a payout. Okay, well, how much should I pay for this contract? I don't know where I'm going to be in the future. Well, remember, we're dealing with this expectation here. This is the equation that we need to solve to figure out the fair price of this contract. So what I can do is run this a whole bunch of times. Maybe I run this 10,000, 50, 100,000 times. And based on all of the places where the stock price ends, I'm just going to take the average value of all of the payoffs of the corresponding options. And that's going to give me the fair price of the option contract. It's going to tell me how much I should pay today for this possibility of a payoff. That is exactly what this equation is telling us. So this is how we go about pricing options in a Black-Scholes framework. In fact, there are a ton of different ways to get to the fair price of this option contract. That is this equation here. And you could do this through solving a partial differential equation. You could do this from approximating a partial differential equation. You could do this through simulation of sample paths like we did here. You could even solve the stochastic differential equation and just find the distribution of stock prices all the way here at time capital T, and that looks exactly like this. And then you can use simulation to produce prices. So there is no shortage of ways to produce a price for this particular option contract in a Black-Scholes framework, okay? And we have a closed form solution in a Black-Scholes framework. So it's very, very quick to be able to produce the price of a European option in a Black-Scholes framework. But we know that we can't use a Black-Scholes framework. We know if we're sitting on a trading desk and we want to extrapolate exotic prices, then we can't use a Black-Scholes model. If you're curious as to why, check out how to price exotic options. Check out how to trade with the option implied volatility surface, the Black-Scholes option implied volatility surface. I have videos dedicated to those ideas. We know that we can't use a Black-Scholes model to quote prices. It doesn't quote consistent prices. If we use a Black-Scholes model, we're going to exhibit arbitrage. So we need a different model. And I've alluded to this idea of a Heston stochastic volatility model. And what a Heston stochastic volatility model is going to do is it's going to assume very similar stock price dynamics as the Black-Scholes model. It's still a multiplicative stochastic differential equation. The only difference is the volatility term here, sigma, is no longer constant. We have this term V now that is a stochastic process itself. So we're actually dealing with two stochastic processes here in a Heston framework. The first is this stock price process. So here is a stock price path. And the second is this variance process. This variance process is assumed to be mean reverting, and it might look something like this when simulated. So we're actually dealing with two stochastic processes that are correlated with one another. This is better capturing the dynamics of volatility in the market. More importantly, unlike the Black-Scholes model, this Heston model will be able to quote consistent prices based on what we observe in the market. This is why we need to go beyond Black-Scholes. If we don't quote consistent prices, then we're going to be quoting prices that may exhibit arbitrage. And over a series of a large number of trades, if you are exposing yourself to arbitrage, you are going to lose a lot of money in this zero-sum game of trading derivatives. To summarize, we can't use a Black-Scholes to quote consistent prices, so we're going to use a Heston model. Okay, what's the problem? Well, unlike the Black-Scholes model, where we have a variety of solutions available to us, in fact, we have a closed form solution available to us, meaning if you just plug in parameters, you get an option price. The Heston model framework does not have a closed form solution. I can't just give you parameters to the Heston model and you give me a price. That would be great, but we don't have a solution to the partial differential equation in that capacity. So what do? Well, just like above here, can't we just simulate paths and then take the average payoff? Can't we just solve this equation numerically by simulating? Yeah, of course we can. That's always an option. And that's actually exactly what I do here. I have a stock price path, I have a variance process path, and I have the corresponding payoff based on where the stock price ends. And if I run this a number of times, you'll see that the option payoff is going to change based on where the stock price path ends. And if I did this 10,000, 100,000, a million times, then I could produce an approximate price. I can take the average of all these payoffs, just like I did above with Black-Scholes, and I can solve that expectation problem. I can tell you the fair value of the contract today based on the Heston model framework. But this is terribly slow. Now, it's not terribly slow in generating one price. We can just simulate a million paths if we have to and produce a price. That's fine. But it's terribly slow if we have to calibrate it to a market surface, a grid of prices. How do you calibrate a model to a grid of prices? You need to solve a minimization problem from calculus. And that's an iterative process. So every time you want to change the parameters of the model to produce new prices, you need to simulate more paths. That's how this works. If I was to change the parameters of this Heston model and I just simulated a million paths, I would need to simulate another million paths and another million paths as I continue to change the parameters of the model framework. And I need those parameters to match the market. That's why this is terribly slow. I'm going to do a video in the future on this calibration process. But the reason why I haven't discussed this calibration process is because this is terribly slow. We need a way to make this pricing faster. Hence, the Fourier inversion and the point of this video. This brings us to the Fourier transform and the place of Fourier transforms in quantitative finance. We're going to talk now about what the heck a Fourier transform is, the idea of a discrete Fourier transform, a fast Fourier transform, and an inverse Fourier transform. Then we're going to talk about characteristic functions, and we're going to combine these ideas then to produce prices for a Heston framework without simulating the paths. It will be significantly faster. It's actually very easy to understand the Fourier transform relative to pricing and quant finance without getting too involved into the Fourier transform itself. The only thing we really have to know is that the Fourier transform is defined by this integral, and it takes some sort of input signal in the time domain, and it maps it to some output signal in the frequency domain. Now, that might sound complicated, but really all we're doing is taking some sort of input, mapping it to an output, and they're going to be one-to-one. In other words, if I take a Heston stock price process in the time domain, then I apply a Fourier transform to that Heston stock price process, and I end up in the frequency domain, well, there's only one Heston stock price process in the frequency domain that matches up to the Heston stock price process in the time domain. So in the Fourier transform sense, all we're doing is taking an input signal, mapping it to an output signal from the time domain to the frequency domain. That's all we're doing when we apply a Fourier transform in this sense. That's really all we need to understand about Fourier transforms if we're going to go about pricing options in a Heston framework. We just need to know that we can go back and forth in that capacity and what it actually means. So now let's talk about practically how we're going to do this. We write the Fourier transform in terms of an integral, but practically we don't operate in a continuous space. We don't have an infinitesimally small quantity or a quantity of infinity on a computer. We have very small and very large, but we don't have infinity. So instead of using an integral, we're going to use a summation. That's all an integral is a continuous summation, right? So we're going to actually operate with what's called a discrete Fourier transform. Nothing changes from our initial intuition about it. We're just mapping an input signal from the time domain to an output signal in the frequency domain. In fact, I have some examples here. I have an example of cyclical functions with different cycle lengths. And what I'm doing is I'm taking this signal from the time domain and I'm mapping it to the frequency domain. And you can see what we're extracting in each case is the cycle length. This is actually particularly useful even in determining economic cycles. There are some applications in time series for determining structure and seasonality, but I will digress and save that for another day. So the discrete Fourier transform is the practical application of the theoretical Fourier transform. The intuition is exactly the same, time to frequency. That's it, some input signal in time to output signal in frequency, and it's one-to-one in that sense. Okay, so is there a way to make the discrete Fourier transform faster? There certainly is. And it's called the fast Fourier transform, or the discrete fast Fourier transform. And it's the exact same idea still. We're going from time to frequency. We have some input signal to some output signal, time to frequency. The only difference here is the time complexity of the algorithm is improved. It's faster relative to the discrete Fourier transform that we saw here. But it's still the exact same transformation. It's the exact same algorithm. Very important to keep that in mind. Okay, so we can apply the fast Fourier transform to go from time to frequency. How do we go back? We know that this is going to map to one thing in the time domain. This frequency domain is going to map to one time domain. This is going to map to one time domain. It's one-to-one in that sense. So how do we go back? Going to use the inverse fast Fourier transform. The inverse fast Fourier transform is going to allow us to take something in the frequency domain and then map it back to the time domain. That's all we're doing here. When we're operating with the Fourier transform in this capacity, we are taking some sort of input signal in time, mapping it to some output signal in frequency, and then if we use the inverse transform, we're going from frequency back to time. We can see it visually here. I have this signal in the time domain. I apply the fast Fourier transform. Now I'm in the frequency domain. Then I apply the inverse fast Fourier transform. Now I'm back in the time domain. It's the exact same original signal. So if we understand this, we understand Fourier transforms sufficiently for pricing in the Heston framework. How on earth is a Fourier transform related to our Heston framework? Well, we need to understand this idea of a characteristic function. And if we understand Fourier transforms, then we pretty much already understand the idea of a characteristic function. Think of something like a dice roll. A dice roll is defined by its probability mass function. That dice roll has a unique characteristic function. Just like the Fourier transform, I can go back and forth. I could go from the dice roll probability mass function to the characteristic function and then back and forth and back and forth. There's only one characteristic function for that dice roll. So if I have the characteristic function of the dice roll, that's the same thing as having the probability mass function of the dice roll. I can go back and forth freely. Same thing is true with a normal distribution. And in fact, I plot it here to show you. I have a normal distribution here. I also have the real and imaginary parts of the characteristic function. If you gave me this chart here, or you gave me these two charts, I would have the exact same information. I could transform the characteristic function back to the normal distribution, or I could transform the normal distribution to the characteristic function. I can go back and forth just like the Fourier transform. So what's actually happening here? Well, let's look at the definition of a characteristic function. We see that it's written in terms of an expectation, and we have this e to the itx, where x is the random variable. It could be a dice roll, a normal distribution, or our stock price process. Well, the expectation is written in terms of an integral. So when I expand this out, what do we get? Doesn't this look exactly like the Fourier transform? This is an integral of e to the itx. It's mathematically equivalent to the Fourier transform. Disregard the sign change. It's mathematically equivalent. Look at the Fourier transform. It's no coincidence that these are roughly equivalent. And doesn't this actually look shockingly similar to the value of our option contract from the start of this video? Didn't we write it in terms of an expectation and an integral? If we go back to the start of this Jupyter Notebook, yeah, this looks very, very similar. And it's no coincidence. There's going to be a very strong connection between all of these ideas, and it's how we're going to go about recovering the option contract price in a Heston framework. So if we understand the idea of a Fourier transform, taking something from the time domain, mapping it to the frequency domain, we understand the idea of a characteristic function being able to map a random variable to its characteristic function and back. We fully understand these ideas sufficiently to be able to use them to price options in a Heston framework. Equivalent to the inverse fast Fourier transform, if you gave me a characteristic function, I could tell you the probability mass or density function of a random variable by applying the Fourier inversion in that sense. I'm recovering the random variable. So you give me a characteristic function, I apply my Fourier inversion, and I'll recover the PMF or the PDF. So you give me the characteristic function of a random variable here, I apply that inversion, and look, I get the original random variable. That's exactly what I did here. I took this random variable, this normal random variable, I applied the Fourier transform to get the characteristic function. This is the real part, this is the imaginary part. And then I just do the Fourier inversion. And I get back from the characteristic function the original PDF. So all we're doing in both of these cases, the cases of the Fourier transform and the characteristic function, is we're mapping something that's one-to-one, meaning there's only one input to one output and one output back to that one input in the time to frequency, or in the sense of the random variables with the characteristic function, the idea of a probability mass or density function to the subsequent characteristic function, and back and forth and back and forth. Now we're ready to approach this seminal work by Carr-Madan. I'm a big enthusiast of this work, so I'm honored to be able to talk about it. Remember, at the start of this video, the option contract, we don't know what state of the world the stock price is going to be in. The best that we can do to determine the fair value is to use an expectation. The expectation of the randomness governed by the model for our framework, a Black-Scholes framework or a Heston framework. In this case, we're dealing with a Heston framework. If we expand the expectation in terms of the definition, then we get this crazy looking integral. Okay, well, we can't solve this integral in closed form. If we could, we wouldn't even be having this conversation. We would just be solving this integral in closed form. Okay, so let's think about what we talked about in this video. What if we apply the Fourier transform? Could we apply a Fourier transform to this? Well, we actually can't. And the reason for that is this option pricing function is not square integrable. We didn't talk about this as a necessary condition for the Fourier transform, all you need to know is if we try to apply the Fourier transform to this call option price, it wouldn't work in the way that we had discussed earlier, where it maps the input signal from time to frequency. It's not going to work if it doesn't satisfy that condition. So is all hope lost? Do we not apply the Fourier transform? Well, Carr-Madan introduced this idea of a damping factor, and it's this exponential term here. And what they're doing is they're just scaling the call price by this exponential factor. So I have this new C term here, which is equal to the product of the original call price times this damping factor. Okay? How does that help? Well, I can apply the Fourier transform now. So I have this modified call price, which is damped by this damping factor, and I can apply the Fourier transform. So if I can apply the Fourier transform, then I can apply the inverse Fourier transform. Time to frequency, frequency back to time. That's all that I'm doing here. So the first stage of this is understanding that if we look at the option pricing problem, we have this expectation, we have this integral. If I wanted to apply the Fourier transform, I can't. It's going to break down. It doesn't satisfy one of the necessary conditions to be able to apply the Fourier transform. So a clever trick. Let's introduce a factor that makes it square integrable, that ensures that we satisfy the necessary conditions for the Fourier transform. That is exactly what we see here. We apply this damping factor, and all of a sudden we can apply the Fourier transform to the call option pricing function. And then if we can apply the Fourier transform, time to frequency, we could go back frequency to time. Why is this such an important idea? Because if we can apply the Fourier transform to option prices and this option pricing function, and we know the characteristic function that governs the randomness of our stock price process, in this case a Heston framework, then we can develop a relationship between the two. And because now we can actually take the Fourier transform and we know the characteristic function of the Heston stock price process, then we can actually just apply the Fourier inversion directly to get the option price. No simulating paths, no approximating PDE solutions via finite differences. We can just go about Fourier inversion of the characteristic function. An absolutely bananas idea. Let's take a look at how we derive this key equation. Essentially, we're starting with this Fourier transform. That's all we're looking at here. This is nothing that we haven't already spoken about. This is the the damped call, C sub t. We're applying the Fourier transform. That's all we're doing here. Okay, if this is the case, we can substitute in the call price formula. That's exactly what we're doing here. This is the original integral that we had for the expectation. That's all we're doing. We're just going to change the order of integration. This is a double integral. We're free to do that. Okay, what does this actually look like? If we evaluate then the inner integral and simplify, then we're left with this characteristic function. Phi sub cap t of u is the characteristic function of the log price process for the Heston framework. Why is this so amazing? Because this is known. This is known in closed form. This is what it's given by. Yeah, it looks crazy, but there's nothing in this equation now that we don't have. Think back to this original integral. If this is the option price, how do you solve this? You don't know what this is. But after applying these crazy transformations, you get to this equation, and you know what everything in it is. Every single term is well defined. You don't have something that you can't solve analytically. Okay, so what do? Well, we just apply the inverse Fourier transform. We're going from this space of what? We applied a Fourier transform. We recognize that, when we apply a Fourier transform, we can substitute in the characteristic function for the Heston log stock prices, and now there's nothing that we don't know. So what we've done is this is essentially what we've done is we're operating in the time space. We can't solve this. So we do a Fourier transform to the frequency space. We switch the order of integration, integrate, and realize, oh, wait a second. In the frequency domain, we can substitute in the characteristic function of the log stock prices. And we're operating in this frequency domain now where everything is defined. Remember, when we were in the time domain, not everything was well defined. We don't know what this is. But when we apply the Fourier transform and we're operating in the frequency domain, everything is well defined. Plug in all the numbers. If I do the inverse transform back to the time domain, I'm just going to get the option prices. That is incredible. That is incredible. We went from time, where we couldn't solve analytically, to frequency, where we can, and then go back to time with the correct solution. That is absolutely bananas, and why I am a Carr-Madan enthusiast. Now, of course, I'm not going to walk through all of the code that implements this. I've already written it out for you. You can check it out on GitHub, the link in the description below on the Quant Guild library, if you would like to price options in this capacity. But one thing to keep in mind is the reason why this result works is because we have the Heston characteristic function of the log stock prices, this giant expression here. If we didn't have this, then we wouldn't know this right-hand side of the equation in the frequency domain. And if we took the inverse Fourier transform, we'd still be left with an unsolvable analytical expression like this one here. So keep that in mind. That's the reason why this works, is because we know what this phi function is. It's given by this guy here. All right. The implementation is difficult. I won't lie to you. The implementation is something that would take quite some time to actually develop. I've done it for you here. I've also written out a general recipe. So if you're trying as an exercise to build the implementation yourself, hopefully this offers you some guidelines. Essentially what we're doing is we're formulating the Heston characteristic function, and we're applying this damping factor to the original call option prices, this key equation that we're developing that introduces a relationship between the log stock prices and the corresponding option prices in a Heston framework. So once we do that, we can discretize this grid. That's for our fast Fourier transform and the inverse fast Fourier transform. And once we do the inverse fast Fourier transform, remember, we're applying it in a sense that is going to allow us to recover the original option prices that we are then going to have to correct because we still apply that damping factor. But that's very easily done because we have it's just an exponential. So we can just apply this correction and we will end up with the correct option prices. Something to keep in mind here is that we are discretizing the Fourier transform. So we're introducing an error anytime we discretize some sort of continuous process. And in this case, we are approximating an integral, right, via summation. And there is this discretization scheme such that these weights are what's called Simpson weights. I'll do another video on quadrature numerical integral approximation in the future if there's interest. It's a very niche topic, so I'm not sure how much appeal there will be, but something to keep in mind as we walk through this example, in the sense that it is exact theoretically, but of course we're going to have some sort of discretization error. And that's what we're going to face anytime we try to go about discretizing some sort of continuous process or operation. So let's take a look at the code here that is being written based on this process, which we discussed above. And the real beast is tackling this Heston characteristic function. So what I've done in this Python code is I've defined these Heston parameters as the parameters for the Heston model that we're trying to calibrate to, say, a market implied volatility surface. And I've defined then the Heston characteristic function in terms of the necessary components along with the Heston parameters. And I've applied the Simpson weights. Again, this is the quadrature. I'll digress, perhaps a video for another day. Then I developed this argument for the fast Fourier transform for the call price. And I use put call parity to produce the put prices based on the call price via the fast Fourier transform. So This is the function that is applying the Carr-Madan argument to the Heston option prices. You could see it's very, very quick. So if I was to run this, you could see I get an option price almost instantaneously. Here is simulation. It's pretty quick, but if I was to do this for a grid, this would certainly be faster. And what I do here is I produce a grid of prices to compare it to Monte Carlo. To see how the accuracy is, I do 80 to 120. You can see they are roughly equivalent, and of course, the Monte Carlo should converge then to the fast Fourier, which should then converge to the theoretical price, of course, assuming the approximation, the discretization of that transform was approaching a continuous space. Some closing thoughts and future topics. Goodness gracious, this was an intricate video to create, but I am an enthusiast of Carr-Madan with my whole heart for a variety of professional and academic reasons. So I'm very happy to be able to do a video on this topic. I hope you enjoyed. I hope you learned something. If you like this video, please like, comment, subscribe. It lets me know that you want to see more content like this in the future. Some future topics that I would like to discuss. Model calibration. I think we are now ready. We've talked about the implied volatility surface. We talked about how to essentially price and trade exotic options, and the only component that we were missing to that entire pipeline was the model calibration step. We just didn't have efficient means of going about calibrating a model. Now we do. So I'd like to talk about calibration. I'd also like to talk about PDE methods for approximating, say, exotic prices. I think those can be also very interesting. I'd also like to use machine learning and neural networks to approximate pricing functionals. I've talked about this in the past. I've done a lot of research on this in a professional setting, so I would like to talk about that topic as well if there's interest. So let me know if you'd like to see any of these ideas in the future, in the near future. I have a long queue, but I'm always interested in adding more based on what you guys want to see. So please let me know. Other than that, thank you guys so much for watching, and I will see you in the next video.